Hi, everybody. Thank you for joining us to the CPAR Dream Seminar. Also, I welcome the guys who are watching us, I think mainly from UC Santa Cruz. Today, our speaker is Abhishek Halder. He's from UC Santa Cruz. He's on the Department of Applied Mathematics and Statistics. Before he held a postdoctoral position at the Department of Mechanical and Aerospace Engineering in UC Irvine, and in the Department of Electrical and Computer Engineering in Texas A&M. He's obtained his bachelor and master's from Indian Institute of Technology in Kharagpur.
Yeah.
Okay. And PhD from Texas A&M, all in aerospace engineering. His research interest is in stochastic systems, control, optimization, and application focus on large-scale cyber physical systems such as smart grid and unmanned aerial traffic management. Welcome.
Thank you, Ron. Thanks for the introduction. Thank you all for having me. So today I'm going to talk about the first computation of what is called reachable tubes for unmanned aerial system traffic management. This is a very recent work that I have been doing with one of my student, Leah Gianforton, who is a scientific computing and applied math student at UC Santa Cruz. In part of this work, I will also describe what are called protocols, specifically one particular protocol called motion protocol for unmanned aerial systems motion traffic management. And that work actually started when I was doing my postdoc at P.R. Kumar's group at Texas A&M in electrical and computer engineering. Yeah. Okay. So when you think about today's manned air traffic management, and if you look into how it's actually managed, it is managed by humans. It's primarily a voice-based system, so there are air traffic control officers. They literally say each and every passenger aircraft pilots that you go 1,000 feet up, you go 1,000 feet down. So, and this kind of system is enforced legally. And the separation management for each aircraft is done through these voice-based systems via these air traffic controllers, who are humans. And this system currently works for what is called control airspaces. These are A, B, C, D, E. So there is some demarcation of the airspace over this continental US. And now what we are talking about in future is what is called UAS, or Unmanned Aerial System Traffic Management. And this is abbreviated as UTM. And here the vision is that in future, we'll have a dedicated traffic management system over the cylindrical airspace over the entire continental US. And this is the plan to incorporate these unmanned aerial systems in the national airspace. And this cylindrical airspace will be part of what is now called Class G airspace, which is deregulated, unregulated right now. And it extends up to actually 1,200 feet above ground level. But the vision is that inside that, within the altitude 200 feet above ground level to 500 feet above ground level, there will be these dedicated traffic management systems where very small drones, which weight no more than 55 pounds, they will fly. And this kind of system, implementing this kind of traffic management system, it requires automated vehicle-to-vehicle separation management, unlike the today's manned air traffic management system. It requires the vehicles to automatically yield to manned traffic, especially near the airports, and avoid obstacles like trees, buildings, towers, and of course dynamic obstacles like other drones. And the motivation behind building these dedicated traffic management systems comes from the fact that it could enable many potential services. And we all have heard about Amazon's plan of 30-minute delivery through what is called Amazon Prime Air. So other than package delivery, there is news coverage. There is interest from CNN for news and sports coverage. And then there is interest in precision agriculture. There is interest in firefighting and more traditional like law enforcement, infrastructure inspection, and also if you're interested in something like real estate photography and things like that. Now, what are the technical challenges in building this kind of system? Now, one of the concepts that has come forth is what is called dynamic geofencing. So this is the picture I'm showing on the top left. So imagine these are some virtual fencing, and this is in 3D, and think of this as virtual fencing on top of the Google map. And this could be space and time varying. So if there is a football game going on, you cannot fly over the football stadium, but if the game is not going on, maybe then that time you are cleared to fly. And then the control should happen over shared communication network. For example, vehicle-to-vehicle communication is envisioned to happen over things like vehicular Wi-Fi, like IEEE 802.11, and then ground station to enterprise to the individual drone communication. So for example, an Amazon drone can talk with an Amazon ground server over cellular LTE. Another challenge is that, so how do you do control over the shared communication medium, and how do you guarantee provable safety or performance of the control systems over the shared medium? So that is one challenge. Another challenge is that there is a real-time wind uncertainty. Even if you plan some path based on wind forecast, the real-time wind, when it does not match with the forecasted wind which was used to plan the path, then how do you actually take that into account to guarantee that in real time no collision happens? So one way to address these problems is by designing what is called protocols. And roughly speaking, you can think of conceptually the protocols as laws of the sky. In the road, we have concepts like lanes, signals, these constructs, and concept like yield. So equivalently, we want to design some protocols that all drones, irrespective of which enterprise and what is their actual business objective, all the drones should abide by. And roughly speaking, you can think of these as 4 categories. There could be more categories like security protocols and so forth. But there should be something like an offline protocol where an FAA server, which could be a centralized server, it approves an incoming flight path request. There should be something like a motion protocol that tells what does an individual drone do, roughly speaking, in real time. And then there should be something like a communication protocol that gives some guideline and what and how should a drone in flight talk, and something like a database protocol where each enterprise maintains a dynamic database that tells each individual drone which other drones to talk with and when. In today's talk, I'm going to focus on only one motion protocol. I'm going to use one protocol that is called motion protocol, and I'm going to use that to motivate the computation of what is called reachable tubes. So to look into motion protocol, we really look into one individual drone's perspective, and we ask the question, what should an individual drone do in real time to guarantee provable safety? Let us say there is already an offline protocol or something like that in place, and that offline protocol tells that each individual drone should fly from the origin point O to some destination point D, and I'm plotting the path as a color, and more blue means it is towards the destination. So the color indicates time. So origin is of course at time t0, initial time, and destination is the final time tf. Okay. Now if there is no uncertainty, probably this would be the picture, and a drone probably will have some onboard controller that will try to track this trajectory as best as it can. Now the reality is that there is some uncertainty. There could be measurement uncertainty coming from communication packet drops. There could be wind uncertainties. Because of uncertainty, there would be evolution of what is called reach sets, and that will give rise to what is called a reachable tube. So the nomenclature is that if we fix a time, reach set describes what are the set of states a drone can reach to. So basically, reach set is the time slice of the reachable tube, right? So I'm drawing it in, of course, this is depicting a 3D situation where the dynamics is in 2D, but time is the 3rd dimension. So the reachable tube is in 3D object, right? But in reality, space is 3D. Time is 1D, so the reachable tube is a 1D object. So time slice of the 4-dimensional space-time tube will be a 3-dimensional reach set, right? If you take the time slice at the final time, so that is that set D in blue, that is the set, the elliptical looking set that encircles the destination point. That set is denoted by the notation R. R means reach set, and the subscript is pi f, meaning if it continues flight. So reach set under the flight mode computed from point O and within the duration from time t0 to tf. Okay. So what are the set of states the drone can reach in tf minus t0 time as computed at point O, right? Now let us assume that there are some discrete decision making instances between this t0 to tf, right? So tf is the final time where the destination will be reached, and t0 is the origin point. And let us say these discrete decision making instances are already computed through some offline optimization, and they basically take into account where the landing spots are. So I'm not going to talk about in detail how this could be computed, But let us just say at the higher level of abstraction that at each of these discrete decision making instances, a drone may either continue flying or it may abort the mission and land. Okay. Now think of engulfing this tube or the reachable tube that I have talked about, this dashed boundary, by an annulus of radius epsilon by 2. What does it do? Well, the uncertainty tells that if the, for example, if the drone experiences worst case wind, it can fly anywhere within the tube. In the worst case, it can be at the boundary of this tube. But let us say you want to enforce a law that no two drones should be epsilon close to each other. Okay. So this tube is basically, or the annulus is basically doing that, engulfing that reachable tube by an annulus of radius epsilon by 2. And I am using the notation that f t0 to t1 is the flight tube from time t0 to t1. And then similarly, flight tube from t1 to t2 is f subscript t1 t2. Similar to flight tube, there should be also landing tubes. So if a drone indeed decides that at time t1 I'm going to land, then there should be some uncertainty. It will also experience wind. So there will be some reachable tube that is described by these dashed boundaries. And again, that is engulfed through epsilon by 2. So just like flight tubes, there are some landing tubes. Just like f t0 t1, there is some l t1 t2 and so forth. All right, so here is the one possible protocol. So the protocol is something that should tell at every time what should an individual drone do. So at t equals to t0, a drone takes off if and only if between t0 to t1, everybody else have said that the drone can take the flight tube between, drone is clear to fly between t0 to t1. So the flight tube between t0 to t1, this green thing is cleared. And also the landing between t1 to t2 is cleared. Okay. When the drone receives that acknowledgement from all possible drones, now all possible doesn't mean that all possible drones in the world, it only means the all possible drones which are near the danger zone of this particular drone, because there is a velocity constant for other drones, right? Then what it does, it then, if it has all positive acknowledgement for flight tube between t0 to t1 and landing tube between t1 to t2, then it transmits request for flight tube between t1 to t2, which is this red tube here, and landing tube between t2 to t3, and then starts flying. Okay. In between t0 to t1, when it is flying within its already cleared flight tube, then it is listening for positive or negative acknowledgements from all drones. And at the moment t1, the moment it arrives at the decision-making instance t1, then it's going to check the condition whether it has received clear to fly or approval or deny from all positive, that is all positive acknowledgements from all other neighboring drones or not. If it has received all positive acknowledgements from the neighboring drones, it is going to do an extra computation. It is going to recompute the reachable tube from that time instance, t1, to see if it has hope to reach the destination point yet. So, the reason for doing that is that it is possible that the newly computed reachable tube, although it is guaranteed to lie within this already computed big tube, but it may miss the destination point. All right. So it's going to check whether everybody else is saying, am I clear to fly? And whether I have hope to reach where I wanted to reach. All right. And if both these conditions are true, it will continue flying, otherwise it will land. Okay. And again, recursively it will do the same things. It will then broadcast request for the next flight tube segments and next to next landing tube segment and etc. Now, if it happens that everybody else has said positive acknowledgements, but the destination D, this is the situation I was describing, D is not contained in the newly computed flight tube because the newly computed reachable reach set at the final time depends on where from you do the computation. So it may miss that point. So in that case, it will abort the mission using the already approved landing tube. All right, so very roughly speaking, the motion protocol, if you think of this protocol as a piece of software that is maybe distributed, some part of it can be on a drones, part of it can be on the ground-based server, and it's basically interacting with what is called communication protocol. So basically from other drones, it is receiving a approval deny sequence, which is a binary sequence, and based on that, it is taking some decision. And if this is a request making drone, it is making the request of some kind of flight tube and landing tube pair, all right? So these are sets. It is making the request in the form of a pair of sets. And if it is, you are a request granting drone, upon receiving such a request, you compute your own flight tube and landing tube pair, and you check whether this flight tube and landing tube pair that is for that particular drone, if it intersects with the request seeking drone. If yes, then you give a deny, or otherwise you give a approval of the request, all right? Now, all of these notions boil down to the fact that, so to enable this kind of protocol, we need to do first computation of the reachable tubes, all right? So by first, what we mean is that the computational time scale for the reachable tube computation should be much smaller than the actual rigid body dynamics time scale, right? So so the idea, another thing that is important here is that probably for the practical, at least for the communication point of view, it will be useful to have some kind of parameterized description of the tube. Why? Because if you have a parameterized description of the tube, because the tube, the content of the tube or the description of the tube is actually the packet content that is going in the communication protocol. So somehow you have to encode this description of the tube in the communication packet content, and from that point you want probably minimum bit length representation of the tube. And this minimum bit length requirement motivates us to think about a ellipsoidal parameterization of the tube. So what we propose here is to compute the tube as not to compute the actual tubes, but instead of computing the actual tubes, to compute actually minimum volume outer ellipsoidal parameterization of the reachable tube. Why ellipsoid? Because ellipsoid corresponds to minimum bit length parameterization. Why outer description? Because we want to be provably safe. You don't want to make a inner approximation. And then why minimum volume? Because although you want to be conservative, you don't want to be too conservative, because that will reduce your throughput of the entire traffic management system. So to guarantee high throughput, we want to do some minimum volume ellipsoidal computation, and it has to be some outer approximation. All right. And for the purpose of the work, I'm going to consider simple linear time varying dynamics, and you can think of the the context in which this linear time varying dynamical system appears is that it can be the linearization of the nonlinear dynamics about some reference trajectory, and this is where the A closed loop T and AT and BT, the system time varying system matrices come from. And they can also come from, when you close the loop, you can have some time varying gain. So time varying also comes from that part. And of course you have some WT, which is disturbance. In this case, these are wind. Okay.
So this is easier for an LTI system, the propagating ellipsoids?
If you do not have any control or any wind, so the ellipsoid remains ellipsoid, of course, even for LTV, right? It could be time varying ellipsoid, but if you have this, then it doesn't remain ellipsoid, even for LTI. Yeah. So setup that I'm going to consider in terms of uncertainty is that I'm going to assume that the initial condition has some ellipsoidal set value description of uncertainty is there. So there is some ellipsoid whose center is vector x0, and matrix capital associated shape matrix of the ellipsoid is capital X0. So X0 is a positive definitive symmetric matrix. And similarly, wind gust has some ellipsoid, and this need not be time, constant in time. It could be time varying. So wind could be time varying. So the ellipsoidal description could be time varying. So roughly speaking, physically, what does it mean? It means the norm of the wind, or the weighted norm of the wind, is bounded, right? So that is the meaning of the ellipsoidal uncertainty. And then input, I put it in the code because the input in the previous page, eta t, it could come from two parts. So when you close the loop, the part of the eta t could be the feed-forward control, and part of it could actually come from the estimation error that you are using to close the loop. All right, so that can also have some ellipsoidal uncertainty, and that will of course again be time varying. So it has some center description. The center of that ellipsoid moves with the vector Vt as a vector trajectory, and there is some matrix trajectory which is capital Vt. So this is the setup I'm going to consider. Now, given this setup and given the previous dynamical description, it is not true that ellipsoid remains ellipsoid. You can write down and set valued integral representation what the set will be, but that just because you can write down a set value description doesn't mean you can compute it. In fact, that expression involves things like Minkowski sum, which is very difficult to compute, especially for high-dimensional system from definition. So to address the question, then we want to address the question, how can I basically compute minimum volume outer ellipsoids of these sets without actually knowing these sets? So the idea of doing this comes from convex analysis. There is a result in convex analysis that says if you have, let's say you have some convex set, there is a unique minimum volume outer ellipsoid for any convex set. Okay, this unique part is not non-obvious. Also, there is a minimum volume inscribed ellipsoid for any convex sets. Now, if you have a non-convex set, you can excuse me, convexify it by taking the convex hull, and then you can have again the same result. This theorem tells little more. This says that not only you have minimum volume inner inscribed ellipsoid, if you scale it up by n, which is the ambient dimension of the space, that scale up is guaranteed to contain the original set. Similarly, if you scale down the minimum volume outer ellipsoid by a factor n, that again is going to guarantee that is going to result in ellipsoid which is strictly inside the original set. And this factor n cannot be improved in general. All right? This bound is tight. So this ellipsoid is this kind of ellipsoids, minimum volume outer ellipsoid MVOE and MVIE. So these are kind of dual descriptions. So we're going to talk about MVOE, minimum volume outer ellipsoid of these sets. And in our context, we're going to compute MVOE for reachable sets. And this kind of ellipsoids are called Lohner-John ellipsoids in convex analysis. And we are going to think about this ellipsoid ELJ as a set-valued operator. So basically, it takes a set, arbitrary convex set. If it is not convex, it just takes the convex hull of the set, and it returns an ellipsoidal set. Now, in general, if you talk about any arbitrary set, computing a Lohner-John ellipsoid is not easy. It is a semi-infinite program because it involves an optimization problem. Because the optimization problem's constraint itself is an optimization problem that takes the set as the input. The good thing about this is that this is a parametric optimization problem because you are going to parameterize using ellipsoid, so you just have to compute one positive definite matrix and one vector, right? You have to describe what is the center of the ellipsoid and what is the shape matrix of the ellipsoid. So our idea to apply this kind of concept in the reachable set over approximation is that we want to construct a parameterized set R hat, which is guaranteed to outer approximate. I think that the inclusion is in the other way. No, it is correct way. No, it is right. So R hat, which will be superset of R. Okay. So I'm going to construct a parameterized set which will be superset of the original set R, original list set R. Now the only complication is that I actually do not know R. I don't know how to compute R. Without actually even computing, I'm going to construct a parameterization which will be a superset. And then of course, if I do the convex hull of it and then take the Lohner-John operator of it, it will preserve the order. All right. Now this parameterization that I'm using is actually proposed by Alex Kurjansky, and there was some collaborative work with Alex Kurjansky with Praveen Varaya in 2010 to 2013. So what Kurjansky proposed is that he proposed to parameterize a set, the ellipsoids, by something called this x plus lit. So think of this, so li0, on top, they are some random unit vectors in n-dimensional space. So he said take some random unit vectors, and based on those random unit vectors, you compute some ellipsoids. And those ellipsoids are defined through some complicated looking equations, and they will define a set of ellipsoids. So for a moment, let's ignore all these details about these equations. So let us first understand what does it give us. So if you suppose you can do this kind of construction, and suppose you can compute a set of ellipsoids through this parameterization, then the guarantee it comes up with is that if you indeed makes this construction and then propagate using the equations he proposed, then if you at any time, any fixed time, if you take intersection of a finite number of such ellipsoids and call that R hat, that set of intersection of ellipsoids, which is not necessarily, of course, not an ellipsoid, but it will be a convex set. But that set will be a superset of the original set. In fact, the guarantee is even stronger that if you keep taking intersections, if you take infinite intersections, you will actually get the set, rich set. Okay. Now this immediately suggests an algorithm. Suppose we can propagate those equations, those are matrix vector equations of this parameterization, and we take, let us say in computer, we take some finite number of parameterization of these ellipsoids, and we propagate these ellipsoids in time, and we take intersection among all this parameterization. Okay, we cannot explicitly compute even the intersection of ellipsoids, but suppose I can compute the Lonergan operator, which is the minimum volume outer ellipsoid of that intersection. Then at every time, this is my over approximation of the rich set, and then I take time union of that, and then apply another Lonergan operator. That is my approximation. That will give me an uniform ellipsoidal tube, outer ellipsoidal tube approximation of minimum volume for my reachable tube. And all of these ellipsoids are in, let's say if it is a rigid body, are in 12-dimensional space, but I can project it back to the 3-dimensional space because I'm interested to define whether there will be any collision or not. So that basically boils down to checking whether two ellipsoidal tubes which are in XYZ, physical XYZ position and time, whether they intersect or not. All right? But of course, I cannot do just XYZ dynamics because dynamics is coupled, so the 12-dimensional nonlinear dynamics will affect my positions. All right? Now it turns out that the computation of Lonergan operator, that is the minimum volume outer ellipsoid of a set of intersecting ellipsoids, let's call it some inner optimization problem. This is over optimization over the parameterizations, and then again there is an optimization over the time. Right? It turns out both of these optimizations can be formulated as semi-definite programming problems. In particular, the inner optimization can be done via what is called S procedure. I'm not going to go into details, so it's not very bad. So it's actually one LMI for this. You take all these input ellipsoids. So input data is that you give a bunch of input ellipsoids. They correspond to your parameterization, and what you get is a ellipsoid, one single ellipsoid, which will be the minimum volume outer ellipsoid of the intersection of this set of ellipsoids. Right? This is the SDP relaxation. And the second problem, that outer optimization problem, corresponds to you input a set of ellipsoids now in time, and you want to compute minimum volume outer ellipsoid of the union of ellipsoids. It turns out to be exact SDP, exact semi-definite programming, so there is no relaxation here. So this is the exact problem, and again, it can be computed as a LMI optimization problem.
What was the relaxation of the previous
Well,
one?
the fact is that so computing the minimum volume, so you give this input data, right? So EI, and you want to compute minimum volume outer ellipsoid of the intersection of a set of ellipsoid. This is a convex optimization problem. It is not known whether this problem is SDP representable or not. Nobody knows this. So there are two ways to handle this situation. One way is you do S procedure. So S procedure says that if you if you solve this optimization procedure, the answer you are going to get is guaranteed to be a over approximation of that. So it is a sufficient condition. It's not a necessary condition. There are other ways of doing it. For example, the Lonergan theorem I mentioned before. This theorem has an extension that says, suppose you cannot compute minimum volume outer ellipsoid, right? Instead, let us say you compute minimum volume inner ellipsoid and you scale it by dimension d. So you can do that. Now it turns out computing the minimum volume inner ellipsoid for a set of intersection of ellipsoid is an SDP problem. So we have done both, but it just seems that in practice S procedure that is less conservative than this just scaling business. All right. Now these, as you can realize, this already because the high dimensional nature of the dynamics, each of these matrices has dimension of the state space. So this is so 12 by 12. But because of symmetry, we gain something. But I mean, still, it is a high-dimensional optimization problem, and there is a lot of LMI for each time. So these are really high-dimensional semi-definite programming problems. We do not hope to solve this on board flight computers. So what we are proposing to actually solve on the ground computer and then upload in time, and hopefully it can be done very fast on ground or cloud-based servers, and it can be done, uploaded in real time. The answer can be uploaded in real time to the individual drones. Now, we do have some ideas to speed up these computations. So there are two, we have two ideas to basically exploit in order to speed up the computation of this, to solve the semi-definite programming problems. One idea is that you can show that this, if you think of ELJ as a loner John as a set-valued operator, it commutes with any linear operator. Okay. The second thing is, of course, it's a trivial result that any nonlinear function, transformation of union is the union of transformation. What that means is that at the end of the day, I'm going to compute, propagate some parameterized, high-dimensional ellipsoid. Now it is the original problem says take the intersection of them, then you compute the minimum volume outer ellipsoid in that high dimension, then you take union of those high-dimensional ellipsoid, then you again compute the minimum volume outer ellipsoid in that again high dimension. At the end of the day, you project. But what this two immediately tells you, you can take the projection operator all the way inside up to here, up to the intersection, right? Now, intersection is a curious business. Of course, in transformation, intersection, I cannot in general interchange unless it is injective. But it is true that projection of intersection, this is a superset of that. Okay, and depending on the shape of the ellipsoid, you may even achieve some equality. So I'm not going to go into details. So all I'm saying is that this motivates computing. You actually do the propagation in high dimensional, original dimensional space, then you immediately project, okay, before solving any SDP. And then you do SDP only over 3-dimensional space, okay, all the SDP, both inner and outer SDP. So that allows you to do some dimensional reduction in both inner and outer SDPs. And the computational framework that we are proposing is this. Notice that this Li, so if you go back to now to this complicated looking parameterized equation that Alex Kurzhansky proposed, actually the vector propagation equation is the center of those ellipsoid propagation equation is simple. It is simply using the dynamics. So this is saying this is a time varying vector. All of these ellipsoids have the same center, but their shape matrices are different. And shape matrices depend on this unit vector Li0 in a very nonlinear way. Now, all of this computation for Li, any computation for any particular Li is independent of any other. That suggests you can parallelize the propagation. So the way we implement this computation is that we take some initial ellipsoid, you choose some random vectors at time 0, a random unit vector, let's say L10, L20, and so forth. And I am using this broken type arrow to show parallelization in computation. So the propagation is parallel in time over this high dimensional space. So propagation is parallel in time. Also in the horizontal direction, we compute this inner SDP across parameterization that can also be parallelized, right? So there are parallelization of the inner SDP and there is also parallelization of the propagation. Now, once this is done, if you really want to compute the outer SDP, then of course you have to wait and collect the data and then do one single optimization problem. So here is some result. I need my cursor. So we implemented for a 12-state quadrotor, linearized about some reference trajectory, and I'll give some details about the simulation setup. And this shows and I'm only showing the result of the inner SDP. I'm not computing the single outer SDP, the last optimization. So this is basically implementing all the parallel computation in time in the propagation and also the parallel computation of the inner SDPs. So, and here I am showing a 2D slice. So the time is in this direction and space, so each vertical size is space. So 2-dimensional space, 1-dimensional time. So this one is easy to visualize because so the tube is actually in 3D, and also I'm changing color. So more red means higher time, but the actual set I'm computing is a 4-dimensional space tube. So space is 3D, but time I cannot plot, so I'm using color. So red means it is higher time. Right, so this computation uses 5 random choice of unit vectors, and here is some simulation detail. So what I'm using is standard quadrotor model with 12 state and 4 controls. So omega is square for each rotor is the control. Wind is only entering in the Fx, Fy, Fz, the 3 aerodynamic force direction, and wind is not entering in any other direction. The controller is a finite horizon LQR tracker. The linearization is about trajectory. So already the open loop itself is time varying, and then again it's also time varying because of I'm closing the loop with a finite horizon LQR tracker. Decision horizon that Tj and Tj minus 1 Tj, so those intervals, the fixed decision making instances I talked about, I took them as 10 seconds. And inner SDP solution I solved it every 2 seconds inside that delta T interval. And we implemented so far, we have not done, I have talked about cloud, so we have planned to do actually in cloud for all this to do two types of parallel computation, but so far we have only done in a desktop computer with CVX and MATLAB parallel computing. Even for this high dimensional system for n equals 3, 5, 7, it takes about 2 to 3 seconds, so which is very promising. I think which basically tells us that we have hope to make the computation almost real time, in the sense that if we go back and look at this, so this picture assumes that computation of this tube is instantaneous in time. So the computational time is 0, only there is a rigid body dynamics time. But to really make it happen, we have to probably start computing a little bit earlier than arriving it here, if you have a non-zero computational time, which is in reality, right? So if you really, this delta T is 10 seconds, we probably start computing, right? At least whatever we have now in our very preliminary implementation, we should start computing 2 seconds, 2 seconds before we actually arrive in this time horizon, decision-making time horizon. So we have some ideas to reduce this time further to sub-second level, so to reduce this time, computational time further, to make it actually in real time. And the idea we have for that is what is called anytime computation in computer science literature. So anytime computation is a model which takes some existing algorithm and it tries to make it a real-time executable algorithm by adjusting the quality of answer, which basically trades off the quality of answer depending on how much computational time you have available. So remember, no matter how many n I have, okay, even if I take 1n, I'm always safe because it is already computing minimum volume outer ellipsoid. By increasing this parameterization n here, I'm basically making the computation more and more tight. So I'm reducing conservatism in my answer. Now, if you do not have enough computational time to do all this parallel execution, then you can get away with much less n, and you can also reduce. So I will not go into details of of the anytime computation, but basically what it is basically what will happen is that if you have less computational time, you are going to give a bigger outer ellipsoids. It will always be guaranteed to be bigger, so it will never compromise safety, but the quality of outer approximation will deteriorate will be variable depending on how much computational time you have available. So that is one idea we want to exploit in this cloud-based implementation. The second idea that we have been working now is that to not use the linear time varying approximation of the actual nonlinear dynamics, but because we are talking about UTM type of application, the original dynamics, nonlinear dynamics itself is differentially flat. So you want to exploit the differential flatness in the computation of the reachable tube. In other words, we want to do the tube computation in the for the feedback linearized system, and then give some guarantees on the size of the ellipsoid. And basically want to say that these ellipsoids will always contain the nonlinear deformed reachable sets that will result from the actual nonlinear systems. Okay, so we want to give formal guarantees on the ellipsoid computation for a system which does not have a LTV structure. That's all I have, and I think I'll stop there and take questions. Yeah.
Is there a way to compute the ratio between the volume of the? Is there a way to compute the ratio between the over approximation and like the actual one? Could you run maybe a trajectory back in time and see whether it got to the something like that?
Yeah. For LTI there is. For LTV it's a little difficult. So we are thinking along the same lines. So basically you are asking what is the guarantees on the quality of approximation, right? For in general there is this kind of guarantees are very difficult to give if you have non-uniform ellipsoidal approximation. in practice, we have seen that we can for example, for LTI, we can actually explicitly compute, and we have seen that 3 to 5, taking 3 or 5, more not, I mean, hardly you need to take 5 different parameterization. Something around the range 3 to 5 parameterization suffice for ellipsoids. Yeah. For general nonlinear system, of course, it depends about the nonlinearity, but in general, we have seen that 3 to 5 suffices. There's not much conservatism there. Yeah.
So in the examples you've shown, the ellipsoid is in the state space.
Mm-hmm.
So it's a 12-dimensional one that you projected to the 2D.
Yeah, 3D. Yeah, 3D and 2D. Yeah.
Okay. So another question I had was, so if you want to do something like platooning,
Yeah.
you have multiple UAVs
Yeah,
close
yeah.
together,
Yeah.
and if you were to reserve such a big space, it would
Yeah.
not be optimal.
Yeah. So. Yeah. So. I mean, I think that question goes beyond a technical question. So. So one thing is that I think at the protocol level, there should be some kind of incentive for everybody to compute good quality approximation for reachable set, because people are, if everybody is doing a very conservative computation, and everybody is saying, okay, I need to reserve this big ellipsoidal tube. Another guy says I need to reserve this much big ellipsoidal tube. Then basically the capacity of the sky is decreasing, right? You want to guarantee the throughput is high. So I think there has to be some kind of incentive or some mechanism. It may or may not be technical. There could be some price-based incentive. So of computing not very large tubes over small, delta t time. But yes, I mean, in general, I mean, as long as there is no guideline, so right now there is no, we do not want everybody to compute very big reachable sets and reserve the space so that nobody else can fly. I mean, so basically it will be first come first serve type of application. So we definitely do not want that. So another thing that I am currently working is actually to ask the inverse question and say, suppose I have some algorithm. It need not be this kind of algorithm. So this is one specific parametric algorithm. If we have some algorithm of computing these tubes in a given volume, what is the capacity for a given type of dynamic? Suppose I have just linear dynamical system. So what is the packing limit for a LTI system? So that will give you some guideline to answer this kind of questions, that if in a given volume, how many, and given some description of uncertainty, what is the maximum number of drones that can be flown? Yeah.
I have a question about this figure.
Yeah.
This is a forward reachable tube, right?
Yeah, this is forward, not backward. Yeah.
Starting from the blue and going to the
Yeah,
red?
yeah.
So most forward reachable tubes I've seen, like, they get bigger over time because there are more places you can go to, and I must have missed something, but why is this getting smaller?
Because the uncertainty is time varying. So one thing it is smaller is its controller in the loop. So it's a stabilizing, number one. Number two is you will see that sometime in between it grows and then it shrinks. So that is because there is a, so the uncertainty description in the wind that I've shown. So these are time varying. This is not constant.
So you're assuming the wind gets nicer over time? Like
no, wind can very fluctuate. So think of it like a diagonal matrix times sine t or cosine t. Okay, so wind can fluctuate. So wind can get strong over time or it can decay over time. Okay, yeah.
So what's happening here is that we are computing the forward reachable tube for a given controller policy, right? For a given feedback policy.
Yes.
All right. So is there any way in which these ellipsoidal techniques can be extended to the case where you haven't prescribed a control input, but rather you're trying to find what your input should be? So you would want to do optimal control.
Yeah, so that's a very good question. If you are by input, if you mean control signal, then the problem is easier. Then it's a control design problem. Then it's basically you have to compute a backward reachable tube of that, and then you basically say that I am here, I want to go hit that set, what should be my control as a function of time? So you think of control as a time. But if you want to think of designing feedback as a policy on the fly, this is a very difficult problem. So then basically it's a so you can there has been some work on this, and so what turns out to be the solution depends on what is called whether your feedback is anticipatory or non-anticipatory. So it's a game theoretic problem, and you basically whether you are anticipating the disturbance or not, it depends on that. So there are two types of game theory problem you need to solve if you want to design the policy itself on the fly, meaning feedback structure on the fly. That's a difficult problem to do. Yeah.
Right. So I was wondering if, in particular, the ellipsoidal techniques could have any usefulness in that domain.
In control,
in
yeah.
the later
So
one that
people have
you're
already done,
describing.
yeah. So there has been some work on that direction to design controllers. So in using ellipsoid, yes, people have already done it. Yeah. Okay.